Hello everyone. Today we are going to see two topics. First is capacitance of an isolated spherical conductor, and second is potential energy of a charged conductor. These are two topics which we have to discuss today. So let's start with capacitance of an isolated spherical conductor. First of all, let's see the diagram. In the diagram we have a spherical conductor of radius small a, and on the surface of conductor plus capital Q charge is given. So due to this charge capital Q, some potential must be produced on the surface of spherical conductor. So we have to actually determine the capacitance of this spherical conductor. So let's start with the derivation. Starting with, if charge q is given on the surface of the conductor, then potential generated on the surface V is equal to 1 upon 4 pi epsilon naught q upon A. This is the expression of electric potential on the surface of a spherical conductor of radius A. If the capacitance of conductor is C, then according to the definition of capacitance, C is equal to Q upon V, total charge on the conductor upon electric potential of the conductor. On solving, we will get C is equal to 4 pi epsilon naught A in farads. If we keep A in meters and epsilon naught in SI units, then we'll get capacitance in farad. From the expression, it is quite clear that capacitance of a spherical conductor is directly proportional to its radius. This is the first topic. And now let's see the second one. The electric potential energy of a charged conductor. Starting with, if a conductor of capacitance C is given a charge Q, then potential of the conductor V is equal to Q upon C. If dq more charge is given to the conductor, then the small work done will be V into dq. On placing the value of V, it will become Q by C dq. So the work done in increasing the charge on the conductor from 0 to Q is the integration of this value. So as you know that C is constant, though, so W is equal to 1 upon C integration Q dq 0 to Q. On doing the integration, 1 upon C Q dq, integration is Q square by 2 with limits 0 to Q. In next line, we are placing the limits. So W is equal to 1 by C into 1 by 2. This 2 is taken out. So 1 by 2, and on placing the limits, it will become Q square minus 0. On solving, it will become W is equal to 1 by 2 Q square by C. This work done is actually equal to the electric potential energy is stored in the conductor. The work done which is required to place Q amount of charge on a conductor will be equal to the electric potential energy stored in the conductor. Therefore, U is equal to 1 by 2 Q square by C. One more expression of Q, that is Q is equal to CV. On placing this value here, you will get U is equal to 1 by 2 CV square. These two expressions are same. This is in terms of Q and C. This is in terms of C and V. Also, if we want to replace C by an expression C is equal to Q by V, U will be equal to half QV. This is the last expression of U in terms of Q and V. So this is all for these two derivations. Thank you.